And welcome to the Experience Geographics Like a Pro webinar. In this webinar, you will be introduced to the new Pro features in Release 2014.1 and the new LMKR Well Planning utility. The Geographics Pro package consists of two new features for 2014.1. The Pro Field Planning, which allows engineers and geologists to quickly create multi-well field plans, and Pro 3D, which allows the users to graphically select a region on a GeoAtlas map and automatically load all the 3D objects on the map, like wells, cross-sections, isomaps, into the scene. Field planning application is designed to reduce the time required for efficient field development. This advanced field planning provides the ability to create, save, analyze, and manage multiple field plan scenarios without having to commit them to the database until you are ready to finalize the plan. When combined with LMKR's well planning, directional surveys, and well prognosis for individual wells or entire scenarios can be easily created, edited, and exported. These capabilities far exceed what is currently out there in the market. We built Field Planner with the emphasis squarely on speed and flexibility. These change rapidly during field planning. Slot locations change. Pad locations, bottom hole locations are updated often due to new surface constraints and the latest subsurface information. All this new information has to be incorporated into the field plan quickly to reduce the cycle time spent consistently replanning well pads. We'll be looking at the Barnett Shale in North Texas for the demonstration and use this reservoir to feature the new Pro tools in the context of an integrated workflow for continuity and context. The demo will start with viewing an integrated unconventional reservoir interpretation that has been created using PRISM for the reservoir characterization and target determination, SeisVision for the velocity modeling and seismic interpretation, and Smart Section for the 3D geomodeling and target surface creation, and finally GeoAtlas for displaying the map of the interpretation and pad locations. Next, a field plan from multiple plans will be created in Field Planner. Multiple well sticks for each pad will be created in Field Planner based upon distance between wells, step-out distance, lateral length, kickoff depth, and reservoir target. LMKR Well Planner will then be used to redefine and define the wells in the plan into an accurate drill-ready design based upon drilling parameters like approach and lateral dogleg severity and drilling geometry algorithm. Finally, the field plan will be visualized in the new Pro 3D visualization application along with isomap surfaces, depth-converted seismic sections and slices, and fence diagrams with interpolated reservoir attributes. You're viewing currently GeoAtlas. On GeoAtlas, I'm showing a number of layers, including 4 different well-based layers, 1 cross-section line of section, 3 isomap layers, 2 cultural layers, and a satellite image. The 3 isomap layers were built from an analysis of the reservoir properties in PRISM and further refine the geometries by using depth-converted seismic horizons from SeisVision, and all converted to depth to display here. Currently, I'm only showing the Barnett target surface. This is the surface that we will be planning the wells along. Also have a satellite image that will show us our pad locations. I've got 4 pads that I will be planning in the field planning demonstration. Pad number 1 down here, pad number 2 to the right, pad number 3 over here on the east, and then pad number 4 in the northeast. Pad number 1 will be the pad that I'll be using for the field planning purposes. Now for performance, I'm going to turn off the satellite image. This toolbar right here is a new Pro toolbar. It consists of icons to launch the new Pro 3D visualization application and our new Field Planner application here. So we'll launch Field Planner. It brings up the Field Planner dialog box. And I'm going to create a new field plan. We'll call it Field Plan number 1. There we go. Field Planner is pretty smart. It knows I've got 4 pads out there that went out and enumerated in the pad list box down here. Now the Geographics pad number 1, that's the one that I'm going to be doing the plan on. I'm going to move it up in here to the scenario pad box. We next look at the slot configurations. We have a number of scenarios we can build from 1 pad, 1 slot per pad, up to 32 wells, 16 wells on a side. For our purposes, I'm going to do the 3-well pad design. Then next I have to define where I want my first pad location as an X and Y location. I can explicitly put those X, Y's in, or I can use this little global tool over here to place my first and last pad locations on pad number 1. It automatically captures the X and Y locations and will interpolate the 3rd well in between the 2. Next, down in the lateral group box, I'm going to use this diagram here to help me define the parameters for the laterals. The spacing is the distance between wells here. The step out length is from the XY of the surface slot location to the landing point. And then the length is going to be the lateral length from the heel to the toe here. So for well spacing, we're going to put in 700 feet. Toe above heel, 10 feet to help it drain the fluids back to be pulled out. Step out length will be 150 feet. Kickoff depth, 3,500 feet. Now these are adjustable. And then heel to toe, 7,000 feet. Now our reservoir target was a surface that we created through the geomodeling, and it was displayed on the ISOMAP layer in GeoAtlas, and it's called the Barnett target surface. Then I'm going to update my layer, zoom out, and zoom into my pad. Now first of all, I see that my azimuths are not correct, so I can easily come back and adjust azimuths or any other parameter, re-update the layer, and then it reflects any changes to the parameters. Now these concentric holes over here are representing collapsed features in the Ellenberger. Ellenberger is a carbonate unit underlying the Barnett, and it's a karsted surface. And these are collapsed features that propagate up through the Barnett and into the Atoka, and they represent geohazards, so it's something we need to avoid. To help us better see our well geometries, I'm going to modify the field plan layer. Now the field plan layer is another layer type created by the field plan tool and can be modified just like any other layer in GeoAtlas. For the well stick buffer, I'm going to change the color to yellow, the weight to 2, and don't forget to turn on the eye here. Now we can better see where these well sticks are extending. Notice they're extending into the area of hazard. So currently I'm going to select the bottom hole location and use the buffers to help me know where to move these back out of harm's way. There. Now this is essentially planned for this pad. I would next return to the field planning tool and then go to the next pad. But for our purposes, we're just going to stick with pad number 1 for design. Now to refine the plan, we've got a new tool. It is called LMKR Well Planner. This is not part of the Pro package, but it's designed to work with both the field planning in GeoAtlas and also individual wells with Smart Section. It recognizes that we've already planned 3 wells for the first pad. So we're going to look at the first slot within the first pad. I've got the surface slot XY and elevation of the pad, the kickoff XY and its subsea elevation, the heel and toe, which was designed along the Barnett target surface, is automatically created here. I click on the Calculate tab, and it shows me a vertical section and a plan view of the planned well. This is the kickoff point, and I'll zoom in here a little bit so you can see a little better. There's my heel point and my toe point created by Field Planner. I've got an isomap surface intersection with the vertical section showing the Atoka surface, the Barnett surface, and the Ellenberger surface. These surfaces are automatically loaded from any isomap layer that was part of the map that's part of our field planning workflow. Now notice that the target surface is not being honored completely because we only have a heel point and a toe point. Now we can digitize other control points or simply put in some guide points here, and it will automatically snap to the target surface right here. Now we can change the approach angle build rates and also the lateral build rates based on the parameters provided by your engineers. And as long as the boreholes depicted here in the vertical section and plan view are in green, this is mechanically doable according to these parameters. Now for example, if I change my geometry algorithm to build and hold, notice I get a very strange looking geometry, but it shows the fact that this kind of algorithm will generate a geometry that shows up red on certain segments here, indicating that it is exceeding the dogleg severity in both the approach and the lateral here. So this well is essentially planned. We're going to look at the display. There's a little cartoon of our display for QC purposes. Now this well is ready to save to the database. But first we can look at what the plan is generated here for our deviation survey, our position log, and our build rate. This can be exported to Excel, so we'll open Excel, and there it generates my targets right here, my deviation survey, my position log, and my dogleg severity. Returning to Field Planner, we're now ready to save this well. So we simply highlight it, right-click, and save this well to the database. And to see that well in WellBase, I'm going to go to the pad. So here's the pad, and it saves it to the new Proposed Survey tab. And we can see this is the saved geometry of the borehole in WellBase. Now at this point, we can go ahead and give the well a name. Call it Gusher number 1, operator GGX, save it. I'm going to close Well Planner and reopen it to refresh it against the new names here. We also have a new GeoProg tab. So here's the well header for Gusher number 1, showing my targets and the formation intercepts down here at the bottom. So this is a prognosis that you can then put into your company's prognosis to help you with your planning purposes, and also as you drill the well, your anticipated intersections. Notice we intersect the Atoka down here and the Barnett 4 times. That's because we are porpoising slightly in and out of the Barnett target surface. This again can be exported to Excel. So here's your prognosis, here's your well targets, and then your formation top intercepts. Now that we've got a drillable plan here, we're going to use the new Pro 3D tool to visualize what we've done. Now, Pro 3D uses the same Xbox gaming technology visualization that Discovery 3D uses. However, the advantage of the new Pro 3D is it allows you to actually select a subset of the area that we want to load into the 3D viewer. So I'm going to draw a selection box over the area that I want to basically cookie cutter out, and any 3D objects within the layers within this extent of this probe will be automatically loaded. So we'll load in the any open well-based layer here, such as the pad that we just built, and it will automatically open or load the 3 isomap surfaces. So I will display in 3D and give this map a name, map number 1. It's launching Pro 3D and automatically loading those surfaces into the scene. Now I'm going to use my Xbox game controller to interact with the scene. This map at the top is exactly the same map as we saw right here displayed in GeoAtlas. The 3 surfaces down here at the bottom are those same isomap surfaces that were loaded on the map in GeoAtlas. I'm going to adjust the exaggeration to see it a little better. Zoom in, and you can see the geometries of the 3 wells in our well plan. The top surface here is the Atoka. I'm going to hide it because we've actually planned the well right along the Barnett target surface right here. I'm going to change the color to make it a little bit more geologically pleasing, and then zoom in right on our well plan here. This is the well plan that we actually built in LMKR Well Planner. I'll make it a little bit thicker for viewing purposes. So there's our well plan, and notice it runs spot along my target surface here. These 2 other wells were part of the field planning well plan, and they landed as a heel point on that surface and truncated or ended as a toe point right here. So these would have to be put into LMKR Well Planner to get this drillable solution right here. Now, I've also done an interpretation in SeisVision, and I built a velocity model, and I'm using that velocity model now to dynamically depth convert a seismic backdrop. And I can put the seismic backdrop and wrap it right along the borehole so you can compare your geometry or borehole to the drilling through the seismic volume. Now, additionally to this, I've got the ability to load and depth convert any seismic section from any volume that I have interpreted in SeisVision. So those are the depth converted, dynamically depth converted based upon the velocity model that I built in SeisVision and displayed in depth. Additionally, you can change the volume. I'm going from an amplitude volume over here to an ESP. This was built in LMKR volume attributes. I did a spectral decomposition and created an ESP volume, which is basically 1 minus semblance. And I'm going to display that as a depth converted depth slice here just right above the Barnett surface. I'm going to change its color palette to gray. It's a little better for looking at discontinuities. We're going to look down on this surface, and you can see these concentric circles representing the collapsed features from the Ellenberger that are working their way up through the Barnett. Go ahead and move this down through the Barnett target surface, and you can see it wrap around those collapsed features. Go ahead and hide the Barnett and continue to work down through the Ellenberger. Now I'm going to remove these surfaces or these depth converted sections by simply clicking on them, remove each one. And then the one wrapped around our borehole. And then return to my map. And I've got a cross section that I built This is the line of section on here, and this is the cross section. This cross section is built in X section, and I've got a gamma ray value here that I'm using the interpolation here, where I'm interpolating a yellow-green palette, a spectral palette, against my gamma ray. So I'm interpolating gamma ray values to indicate where I've got shale, it's a dark green color, and where I have non-shale, it's more this yellow color. Then going back to my map with the line of section and the section of wells turned on as well-based layers, let's display that in 3D. Just going to refresh my Pro 3D visualization. There we go. Come around here and zoom into the area of my fence diagram. And for clarity, I'm again going to hide the isomap layers. Zoom down in here, and you can see the interpolated log curve values along the face of the line of section. I can also display the log templates that I used inside of X section to display the gamma ray values. And I'll swing down here, and I want to show you what good high resolution and high definition we're getting with this technology. There you can see this is the prism log template that we used to build the cross section in X section, and you can see it's very high resolution. Now I'm going to zoom back out because I want to display a depth converted seismic section right along the face of the fence diagram, and then use the transparency on our cross section to blend out the petrophysical attributes so you can see the effect of the geophysical amplitudes in this case against the cross section. Now the last thing I want to show you is our ability to drape any available map on the structural surface. So this again is my Barnett target surface, so select that as my active surface, and I can drape any map. In this case I'm just going to drape the map that I've got in GeoAtlas right along that surface. So any map that you build and revealed here becomes available for displaying as a overlay on any structural surface. Now currently these are all isomap structural surfaces. We have plans next year to also incorporate this visualization in the smart section where we can see frame builder surfaces and also smart section cross sections. So in conclusion, Geographics 2014.1 with the new Pro Field Planning and 3D visualization along with the new LMKR well planning tool enables quick and easy creation of multi-pad, multi-well field plans that are accurate and mechanically drillable. The field and well plans along with other 3D objects like wells, structural layers, and fence diagrams can be quickly selected from a map region and automatically loaded into our new high-performance, high-resolution 3D visualization environment. Pro 3D also displays an interpolated petrophysical attribute along the fence diagrams and dynamically depth-converted seismic sections and slices from any available seismic volume. To complete the visualization, any map can be draped upon any structural surface to show the relationship between structure and map features.